Okay, in 6.4, we're going to talk about inequalities in one triangle. And looking at one triangle, there's a few theorems, and our goals today are just to state and apply the inequality theorems and corollaries for one triangle. And ultimately, in the next lesson, we're going to compare those with inequalities theorems for two triangles. Taking what we already know, we know that an isosceles triangle has congruent base angles as long as the sides opposite them are congruent. So between AC and AB we have 12 and 12, therefore angles C and B are congruent. Well, what happens when we actually make them not congruent? RT is greater than RS. Therefore, what could you figure out about the angles of S and T that would make you think that one could be greater than, less than, or congruent to each other? Theorem 6.2 says that if the side of one triangle is longer than the side of a second, then the angle opposite the first side is larger than the angle opposite the second side. And we could obviously throw in there, based on the fact that a triangle has three sides, we could then conclude that there's a small, a medium, and a large side. 5 is opposite the largest angle, 3 is opposite the smallest, and therefore 4 would be in the middle. Take a second, hit pause, and answer questions 1 through 8 on your packet now. The next theorem we're going to talk about is basically the converse of that, where if one angle of a triangle is larger than the second angle, then the side opposite the first angle is longer than the side opposite the second angle. Looking here, if we knew that angle S was greater than angle R, we could then say that side TR is greater than side TS because the angles opposite them have an inequality amongst them. Looking at examples 9, 10, 11, and 12, see if you can figure out the longest and shortest side of each of these triangles. Hit pause and do that now. There's two corollaries involved with lesson 6.4, and they seem sort of self-explanatory. The perpendicular segment from a point S to a line TR is the shortest segment from that line to the point. It goes without saying that the shortest distance between a point and a line from the previous theorems is that one that's perpendicular. So RS would be longer than the purple line, and obviously ST would be longer than the purple line. And so that corollary is involved there. We can also apply the same thing from a point to a plane, and the point to a plane, that line that is perpendicular from the point to the plane is the shortest segment from the point to the plane. And we could prove that by taking another line and connecting it like you see. That line here is definitely longer than the perpendicular one. Looking at those two corollaries plus the previous theorems, go ahead and answer questions 13 through 20. The final theorem in lesson 6.4 is the triangle inequality theorem. That's the name of the theorem. And it states that the sum of two lengths of any sides of the triangle has to be greater than the third. Looking here, if we have AC plus CB, 5 plus 3 must be greater than the third side of 7. Therefore, we know that we could create a triangle. But it's not just any two. It has to be all three combined. So 5 plus 7 must be greater than 3, 3 plus 7 must be greater than 5, and 5 plus 3 must be greater than 8. It can't just work for any pair. It has to work for all the pairs of those three sides. Taking a look at this example here, why wouldn't it work for a triangle that would have sides of 2, 4, and 6? Take a second and see if you could explain why that would be true. Taking side 2 and dragging it to and connecting with, say, side 4 at the top here, if I were to try to create another angle with that and connect the end segments, both here and here, to the end segments of here and here, for that 6 centimeter or 6 unit segment, I would be basically making one straight line because 2 plus 4 equals 6. It's not greater than 6. And there's got to be room somewhere for an angle to be created from segment 4 and segment 2. So there's got to be some way that we can create an angle at this vertex here. And because it's 2 plus 4 making 6, these ends here of the segment must connect to these ends both here and here. And there's no room for an angle to be a vertex and create it in between the 2 and the 4. Therefore, it doesn't work. So it must be greater than. Taking a look here, find the possible range of values to be answers for x in terms of what side lengths are possible. So looking at the triangle inequality theorem, we could then say 5 plus 9 must be greater than x, therefore x has to be less than 14. We could say that 5 plus x must be greater than 9, therefore x must be greater than 4. And then we could say that x plus 9 must be greater than 5. Well, that's sort of built in, but x can't be greater than -4 because then that would give a negative segment as a possibility. Now, this algebra doesn't work for a negative sign for every single segment, but we obviously know that it can't have that possibility. Plus, looking at these two, x must be greater than 4, but it has to be less than 14. So the possibilities are in between 4 and 14. That's your options there, and every time you see a possibility for x, it has to be between those two numbers. Looking at the triangles here, I want you to identify the largest and the smallest angles in the triangle, and also do the same for the largest and shortest sides of the triangle. Do that now, please. Hopefully you found that the largest and smallest angles of the triangle are angles I as the largest and angle J as the smallest. The largest and shortest sides would be ST as the longest and RS as the shortest. Going on, answer the following. Is it possible to have a triangle with the sides indicated as side lengths? Hit pause and answer A and B now. In letter A, 6 plus 8 is 14 greater than 10, 6 plus 10 is 16 greater than 8, and 8 plus 10 is 18 greater than 6. Therefore, you are able to make a triangle out of that. Letter B, 3 plus 4 is 7, not greater than 8. Therefore, you cannot make a triangle with side lengths of that. Take a second and answer questions C, D, and E to determine whether a triangle could be made based on those segments. Question C is yes. Question D is no. And question E is yes. Moving on. The lengths of two sides of a triangle are 8 and 13. Write a compound inequality that would represent the lengths. Please also read the second question with the algebraic value of y for one of them and y plus 2, and see if you can come up with two compound inequalities for those two questions. For the first one, 8 and 13, your compound inequality should read something like 5 is less than x, which is less than 21. Which means the value of x and the side length of that third side can be between 5 and 21. On the second one, you can have a value for your third side as x in terms of y being something greater than 2 or less than 2y plus 2. Not knowing what y is, the only thing we can do is write our answer in terms of y. At this time, please finish answering questions 21 through 28. Have them ready to finish for Monday.